Kia ora tātou, and welcome back to another week of Biophysical Principles. Now, in this next couple of weeks, we're going to be concerning ourselves with things that oscillate. So you've probably jumped on a trampoline before, and when you kind of get sick of that and you just stop, you keep bouncing up and down as it sort of comes to rest on the trampoline for a while afterwards. Or maybe in keeping with that same playground theme, you're on a swing and you stop pushing, but you don't immediately stop swinging. You naturally swing backwards and forwards. Or perhaps you've been bored in class and you just got your ruler and you sort of clamped it, this is my ruler, on a desk, and you can boing it up and down and it just keeps oscillating, i.e. it's moving up and down repetitively. So what we're going to do in this lecture is our goal is to get our head around some of the mathematics that we need to describe these kinds of oscillations. Okay, so if we could have a mathematical description, then we'd be a long way towards sort of beginning to understand how they work. And as part of that, we're going to familiarize ourselves with a bunch of terminology around these things. Things like periodic motion, amplitude, frequency, period, and angular frequency. Okay, so let's get to it. So earlier in the course, we got you to do an exercise where you had the unit circle, which, remember, that's a circle of radius 1 centered at the origin. And so we showed that if we mark on a point at a certain angle from the origin, we saw that the x-coordinate of that point was always cosine theta, and the y-coordinate of the point was always sine theta. Okay, so this is a really important connection to keep in mind, and you can almost take this to be the definition of what cosine and sine actually are. So I've made a little applet here to help sort of demonstrate this. So as I move this angle slider around, you can see that my point on the circle is moving around and the angle is marked down there. So for example, if I put in an angle of 30 degrees, I can read off my x-coordinate, which is our cosine theta in blue there, as about 0.87. And my y-coordinate is 0.5. We can read that off there in green. So what we're going to do this time to kind of move forward from that exercise we did in class is to actually draw these as graphs. So I'm going to set up some axes with my horizontal axis being the angle theta, and I'm going to set up my vertical axis to be ranging between -1 and 1. So what I'm going to do is I'm going to sketch on some points on the graph as I move this point on the circle around. So let's set it back to 0. Okay, so I'm going to start by marking on the cosine and sine points on my graph for an angle of 0. I'll do my graph in blue for cosine theta and green for sine theta. So when the angle is 0, cosine theta is just 1. You can see my x-coordinate there is just 1, and my y-coordinate is 0, so I'll mark that on my sine graph. So let's just, we're going to go all the way around the circle, so maybe we'll do it in increments of about 45 degrees. So let's jump ahead to 45. Once we've got to 45, you can see that the cosine curve has come down to about 0.71. And the sine curve has come up to about 0.71. So we can mark those 2 points on our axes and continue. So now I'm going to continue on to 90 degrees. And here we can see that my cosine has dropped right away to 0. My sine is now at 1, so I'm just going to mark them on my graphs. Let's continue to the next one, which will be 135. There we go. So you can see we've got now cosine is -0.71, sine is 0.71. Continue on to 180. Now cosine has got all the way around to -1. Sine is back to 0. 225. We'll have -0.71 and -0.71. 270. Almost there. Cosine is now 0 again. Sine is -1. 2 more. 315. Is going to give us those 0.71s again, so it's 0.71 for cosine and -0.71 for sine. And then finally 360, it's off the edge of the page, let's just scroll that slightly, is going to be back where we started, and so cosine has returned to 1 and sine is back to 0. Okay, so what you can see is that the resulting curves have this kind of wavy shape, and we call these sinusoidal curves. So the two functions, which are called sine and cosine, they're kind of similar. They look kind of the same, except that cosine starts at 1 and goes down first, whereas sine starts at 0 and goes upward as the angle increases. So otherwise they sort of do the same kind of behavior, it's just they have different starting points. So it's particularly important to be familiar with what each curve does at multiples of 90 degrees. So I'd recommend you have just a bit of a think about this and try and fix in your head what these two different curves are going to do when the angle is 90, 180, 270, and 0. Okay, so that's kind of our sinusoidal graphs. Now the next thing we're going to cover that we didn't do earlier on is radians, and these are a better measurement of angles for actually doing mathematics with. Okay, what might be a radian, you might ask? Well, let's return to our sketch of the unit circle. So once again, we'll put on an angle of theta. Now it seems really strange at first, but usually mathematicians and scientists use a different kind of measurement of angles, which can be thought of as the distance around the unit circle from the positive x-axis, rather than that angle in degrees. So it sort of makes sense. If I increase my angle, that distance is going to increase. So the two things are in correspondence with each other. If I'm measuring my angle that way, these units of angles are called radians. Okay, so our first job might be to figure out how these actually relate to the degrees that we're more used to. Well, we do know that the total distance around the circle is 2 pi. That's because the circumference is pi times the diameter, which is 2 here. So that means an angle of 360 degrees, i.e. a full turn, must equal 2 pi radians. So we can figure out other angles just by taking proportions. 90 degrees, well that must be 2 pi over 4 radians. That's because 90 degrees is 360 degrees over 4. This also means that 1 degree must be 2 pi over 360, which is the same as pi over 180 radians, and conversely that 1 radian has to be 180 degrees over pi. So to convert an angle from degrees to radians, therefore, all we have to do is multiply it by pi over 180. And likewise, if we want to convert an angle from radians to degrees, we would instead multiply it by 180 over pi. Now there's one other little oddity that we have to be aware of. Formally, radians actually are dimensionless. They don't have any units at all. But we often write the units down as radians or rad, kind of just to remind ourselves that we're referring to an angle, but technically there isn't actually any unit for radians. Okay, so we should practice this before we move on. So let's do a few quick examples. So once I've written down the questions, you might want to pause the video and have a go at figuring them out yourself before we give you the answers. So see if you can figure out the following angles. Number 1. Convert 30 degrees, 60 degrees, and 135 degrees to radians. And number 2, can you convert pi over 4, 2 pi over 3, and pi radians to degrees? Okay, now hopefully, I'll just do a couple of them. 30 degrees, well that's going to be 30 times pi over 180, which works out to be pi over 6 radians. Doing the same kind of thing, you'll get 60 degrees is pi over 3, 135 degrees is 3 pi over 4. Notice I'm simplifying my fractions as I go here. And finally, doing it the other way around, pi over 4 radians, well, I multiply that by 180 over pi, which will give me 180 over 4, which is 45 degrees. By the same token, 2 pi over 3 radians, that's 120 degrees, and pi radians, that's 180 degrees. Okay, one other thing we should say before we move on from this is when do we actually use degrees and when should we use radians? Well, generally we use the radians when we're working out mathematical problems. But the problem with radians is they're far more difficult to kind of intuitively conceptualize. If I asked you to visualize an angle of 1.57 radians, and then I asked you to visualize an angle of 90 degrees, the angle in degrees is probably much easier for you to kind of build a mental picture of. So generally, we use degrees when we want to clearly communicate angles to a reader. What this means is that a problem is likely to be specified with an angle in degrees, and it's usually good to present your final results in degrees as well because they're much easier to understand. However, when it comes to actually working out problems mathematically, it's usually best, and something you should get into the habit of, to work all angles in radians. So that might involve some conversions at the start of your problem. Now, and also worth noting that for all the work that we're going to do with periodic motion, we will treat the sine and cosine functions as just taking input in radians only. Okay, finally, when you're using your calculator, you need to make sure that your trig functions are expecting radians or degrees depending on what you're doing. So you'll need to be familiar with how to switch modes. So I'll demonstrate quickly on my Casio graphical calculator. All I have to do is enter the run mode. And then I go into setup, which is shift menu. And then I can set my angle property by scrolling down and hitting F1 to turn it to degrees, or F2 for radians. Don't worry about the grad option that your calculator offers as well. These are kind of obsolete and they're not used in science. Some very specialized areas, I believe, occasionally use these, but don't worry about them. Right, so how are we going to use our newfound knowledge? Well, we're going to start with sort of the basic prototype of an oscillating system, which is the mass on a spring. Now, I couldn't find anything lying around my house that I could use, so I'm going to cheat and use a PhET simulation to kind of demonstrate this. So the basic setup is simple. We've got a mass and we've got a spring, and that's pretty much it. So let's just hook this mass onto the spring here, and you can see that I can drag it up and down, and when I let go, probably what's going to happen is you expect that if I start it at the bottom, or maybe start at the top, then it will initially drop and then get pulled back by the spring and then sort of oscillate indefinitely. And yep, there it goes. So maybe I'll make it a little bit smaller so I can catch it. Stop. And so this time I'll start it from a little bit, say, in a distance. There we go. So you can see that this mass just basically bobs up and down. You may have seen those kids' toys that you hang from the ceiling and that have sort of these animals that bounce up and down. It's pretty much exactly the same concept. Okay, so we could see how we might go about setting up an equation for this mass on the spring. So at any given moment, there are only a couple of forces that are actually acting on this mass. There's always going to be that gravitational force. I'll just stop it for a second, which is going to be acting downwards. And there's going to be a force from the spring, which, depending on whereabouts the mass actually is going to act up or downwards. So if my mass, let's just imagine that it's on the part of its cycle where it is moving upwards. Okay, so it's moving up here. The spring is going to be pushing on it downwards, which means its net acceleration is actually going to be in the downwards direction. That's why the mass sort of slows to a halt, turns around and ends up going down again. But then when it sort of passes its equilibrium or halfway point, as it's going down, the spring is now going to be pulling back up on it, and so the acceleration is going to be upwards. So what we see is that the acceleration of the object is kind of always against the motion, or mostly against the motion of it. And so you can see that there's sort of out of syncness of the acceleration and the actual motion of the thing leads us to this backwards and forwards behavior. Okay, so if you go on to study further physics or mathematics, you'll learn how to derive the actual equation for the system and link it, and things like how long it takes to oscillate and all that kind of thing. You can figure out what those numbers are in terms of things like the actual mass itself and the spring constant of the spring in question. Anyway, what we're going to do is a little bit simpler. We just want a sort of description of this motion. We don't want to necessarily build an equation for how it physically comes about. So we're going to imagine that we're plotting this displacement of the mass as a function of time. So at every instant in time, it's like we're going to take a photo and then record the displacement of our mass. So we'll just treat positive displacements as being upwards, and we're going to imagine that we start with our mass at a positive displacement and that we're going to drop it and see what happens. So what will happen is once we let go, it will head downwards for a while. So after a little bit of time, it will be a little bit lower than where it started, and it'll keep on going downwards. It'll cross some kind of halfway mark, keep on going down, and at some moment in time, it's going to hit this minimum value down here, and then at some further moment in time, it's going to now be going up again, and overall, you'll see that the thing just goes up, down, indefinitely. Now, if I were to sort of plot this out, then what we see is a sinusoidal shape, just like we saw before with our unit circle, which is pretty cool, given that we just learned about what those are. Okay, so let's sketch our graph a little bit bigger, and we're going to try and draw the graph of this motion and figure out what an equation for it might be, or what it might look like. Okay, so instead of having the angle on the horizontal axis, this time we are going to have the time on the horizontal axis. And we started our motion at the top, so it's going to start up and you're going to see a sinusoidal shape that looks a bit like our cosine function from before. Okay, so our horizontal axis is now time, it's no longer radians, and our vertical axis, well, it no longer goes between -1 and 1. Now it goes between two fixed values, assuming 0 is the halfway mark, which we can call -a and a. So now we can kind of come up with our mathematical description of this motion. So we know that the cosine function itself, that just goes between 1 and -1, because that was our x-coordinate on the circle before. So given that our motion actually goes between a and -a, it seems like our function should just be a cosine multiplied by a. Something like x, where x is the displacement, is going to be a times the cosine of little a times t, where we still need to figure out what little a might be. Alright, so now's the time to introduce some terminology. The value capital A is called the amplitude of the oscillation. So it's half of the peak-to-peak distance vertically on our picture. The period, which we usually write with a capital T, of the oscillation is the time taken for the mass to complete one full oscillation. So you can read this off a graph quite easily as the distance between two of the peaks, or between two of the zero crossings that are going in the same direction. And period is usually measured in seconds if we're in SI units. Okay, now the next one is the frequency, and we usually write that with a lowercase f, and the units of frequency is hertz, is the number of oscillations per second. Okay, number of complete cycles this mass goes through in 1 second. So if the period was 0.1 seconds, if it was a very fast spring, then you'd have, well, it must be 10 cycles in a second if the period was 0.1. So our frequency in that case would be 10 hertz. So in general, you can get the frequency by just taking the reciprocal of the period, i.e. 1 over the period. So that gives us the equations f is 1 over t, and it goes the other way as well. You can get the period from the frequency by calculating t is equal to 1 over f. Okay, and the final concept is that of the angular frequency. Now we usually write that with an omega, so it's the Greek letter omega, not a W. Sometimes with handwriting it's hard to tell the difference, but omega, or the angular frequency, is the number of radians that are gone through every second. Okay, so its units are radians per second, or just per second, because remember radians aren't actually real units at all. So each cycle has 2 pi radians, so for every cycle there must be 2 pi radians, and so if there are 10 cycles a second, there must be 10 times 2 pi radians a second. So our angular frequency omega is just 2 pi times the frequency itself. Alright, so let's get back to our mass on the spring. So we decided that our formula should look something like x is equal to a times cosine of little a times t, where we have no idea what little a is yet. That was just an educated guess that it might look like that. Okay, what do we know about cosine? Well, the cosine function cos theta itself, well, that completes one whole cycle when the input to cosine, that's theta, gets to 2 pi. So remember, it starts at 0. By the time the angle gets to 2 pi, which is 360 degrees, then we've completed one whole cycle. Now also for our spring, our mass on the spring, if we've measured our period, we know that our first oscillation is complete when our time is equal to that period t for the first time. So that means that at, little a times t, should equal 2 pi when our little t is equal to our big T. So if we substitute that in, we'll get little a times big T must be 2 times pi. Now remember, a is the thing that we actually didn't know what it was, so we can solve this to give us little a is 2 pi over big T, or 2 pi over the period. Okay, so our description is now pretty much complete if we substitute this value of a into our previous expression. So we'll get x is equal to capital A, that's the amplitude, remember, times cosine of 2 pi over the period, 2 pi over big T, all times t. And finally, we can express it in terms of our frequency or angular frequency instead by using those relationships from before. So the following three expressions are all completely equivalent. First one is x is equal to a cos 2 pi over t, the one we just did. If I use f equals 1 over t, I can replace that by x is equal to a times the cosine of 2 pi times f times t. And if I replace 2 pi f with an omega, it's also the same thing as x is equal to a times cosine of omega t. Okay, now with all of these examples, we've started our oscillation at the top and dropped the mass. Okay, so it started at A and went downwards. If it started at 0 and went up, we could use sine instead, because remember, sine starts at 0 and goes upwards initially. And if it started somewhere in between, then there are some modifications we can do to our equation to make it work, but we're not really going to worry about that level of detail at the moment in this course. Okay, the key things we want to be comfortable with are the frequency, the period, and the angular frequency, and how to get them from that description. So let's finish off with an exercise. So what I want you to do is to find the frequency, the angular frequency, and the period of the following oscillation, represented by y is equal to 7 times sine of 10 pi times t. Okay, so once again, you want to pause this video and try figure out those three things yourself before you play further on. All right, so let's read the values off. So we can get the amplitude by just reading off the number in front. So the amplitude is 7. The angular frequency, that's the next easiest one to get because it's just the number. It turns out it's just the number in front of t. So the angular frequency is omega is equal to 10 pi. Then the frequency, well, that just divide the angular frequency by 2 pi will give us that f is equal to 5 hertz. Frequency is 5 hertz. And finally, the period, which is 1 over f, must be 0.2 seconds. Okay, so I think we've covered a good amount of ground for today. So I think that's probably about enough. We will catch you in the next one. Ka kite anō.